So this is a question from the 2009 BC exam. This is problem number 3, and this is a calculator question. And the situation that's described here is that a diver is on a platform. They're leaping off the platform, traveling along this path into the water. We're told that t is being measured in seconds, and x of t is going to represent the horizontal distance between the platform and the diver's shoulders, and y of t is going to represent the vertical distance between the water and the diver's shoulders. We're told that the diver's shoulders begin at 11.4 meters above the water, so I labeled that on the diagram here. And what we're given to work with is the x component of velocity, right, the rate of change of the x component of the diver's shoulders, and then also the rate of change of the y component of the diver's shoulders. So we're given the x component of velocity and the y component of velocity to work with. We're told that A is the time when the diver's shoulders enter the water. And then in part A, what we want to do is we want to find the maximum vertical distance from the water to the diver's shoulders. So we want to know what the y coordinate is at the peak of the dive. If you think about this, there are a couple different ways that you can approach this. I approached it from a graphical standpoint, and I said, well, you know, at this point, the slope of my tangent line to the curve that represents the diver's path is 0. So what I did is I set the slope of the tangent line equal to 0, which is going to be, when your curve's defined parametrically, dy dt over dx dt. And that is only ever going to be 0 when the numerator is 0 and the denominator is not. So I needed to know when dy dt is equal to 0. Now if you take a physics approach to this, you can say, well, the peak is going to happen when the y component of velocity is 0. Right? The object is no longer increasing in height. The object is not yet decreasing in height. It's at that one moment in time when the vertical position of the object would be considered stationary. And so either way, you're going to have to eventually set dy dt equal to 0. You set dy dt equal to 0. You solve for t, and you get 0.367. So that's the time when the diver is as high above the surface of the water as they ever get. And then if you want to figure out what that maximum distance is, you want to know the y value at this time. So that's going to be found by taking the initial y value, the 11.4 meters above the water that we started at, plus how much the y component of position increases between 0 and 0.367. And to figure that out, we're going to integrate the rate of change of the y component of position, take the sum, do this integral on the calculator. I guess this is one you could do by hand. You can find an antiderivative for dy dt here, but since the calculator's in play, you might as well evaluate this numerically on the calculator, and you get 12.061 meters above the surface of the water for that maximum y value. In part B, it wants us to figure out what A actually is. What is the time when the diver's shoulders enter the water? And so what I realized was, well, at this point, the y coordinate of the diver's shoulders is 0. So I needed to know when y was 0. So what I did was I found my formula for y of t. You know, I had to take an antiderivative of this. So I take the antiderivative of this, and what that gives me is 3.6t minus 9.8 over 2t squared. And then I have to tack on my constant c. And then if you try to find c, you know when t is 0, so if you put a 0 here, you put a 0 here, you know the y value is 11.4, and that's going to tell you that c is 11.4. So here's a formula for the y coordinate of the diver's shoulders at any time t. You want to know when that value is 0, so you set that equal to 0, and again, the calculator is in place, so there's no sense in using the quadratic formula here. You can go ahead and solve this graphically. So if you graph this in function mode and then figure out when that graph was equal to 0, you get about 1.936. In part C, it wants us to find the total distance traveled by the diver's shoulders from the time that she leaps until she enters the water, and that's going to involve integrating speed across the entire time frame of the dive. And the speed formula when you're dealing with parametric equations is just the formula for the magnitude of the velocity vector at any time t. So that's going to be the x component of velocity squared plus the y component of velocity squared, all under a square root from the Pythagorean theorem. We're going to have to integrate that from 0 up to a, and remember a was our answer for part B, that 1.9 whatever. And if you do this integral on the calculator, and you have to be really, really careful with your grouping symbols here, but if you do this integral on the calculator, what you end up with is you end up with 12.942 for the total number of meters that the diver's shoulders traveled through as they went through this dive. And then in part D, this is a part that's kind of different. You don't have this in a lot of other free response questions. It wants us to find the angle theta, which is between 0 and pi by 2, or 0 and 90 degrees, between the path of the diver and the water at the instant the diver's shoulders enter the water. So the diver's entering the water right here, and it's happening at a certain angle, and we want to figure out what that angle actually is. So what I recognized is if I could find the slope of the tangent line at the moment the diver enters the water by doing dy dt evaluated at A, so evaluate this at that 1.9 that we found in part B, also evaluate dx dt at A, and there's no t to put that value in place of here, so it would just be divided by 0.8. What you end up with for the slope of the tangent line is negative 19.216. So we have a really, really steep slope as the diver enters the water. Well, if you use rise over run, that means to get from this point to this point, and assuming this is the point where the diver's shoulders enter the water, we have a rise of negative 19.216 and a run of positive 1. And I want to know what this angle theta is right here. So if I just do a little SOHCAHTOA work here, just a little simple trigonometry, I'm going to end up with opposite and adjacent. So tangent of theta has to equal 19.216 over 1. And then if I want to solve that for theta, I'm going to do the inverse tangent of 19.216. And what I end up with is I end up with 1.519 radians. And if you think about this number of radians, pi by 2, that's 3.14 divided by 2. That's about 1.57. We have a number of radians that's really, really close to that. And that should make sense. We almost have a 90-degree angle or a 1.57 radian angle at the moment when the diver enters the water.